What am I doing today? Okay. Just planning to read a paper on basically this why machine learning struggles with causality paper. Something that's right up my alley. And see if I can't get all my streaming stuff online here. I got one of these things. Just trying to figure out the whole streaming thing. I got this piece of hardware here that will ostensibly allow me to press buttons and make things work. But that requires me to actually take time out to actually set the thing up, which it's unlikely to happen anytime soon. Let's see here. So it's like a million things that needs happening. Okay. There's some other more people or more machine learning people are showing up onto volume down on that. Showing up on the streams. Steve Wolfram is one of them. Started watching his stream recently. It's mostly like a Zoom conference, like a webinar, but it's interesting. He's probably more adept at this stuff than I am. Let's see if I can't switch screens here. Why is it showing Skype? All right. All right, so great. This is a blog post that was inspired by this paper by Shokov and Bengio and others. And so, I think Yoshua Bengio is interesting in how he's trying to talk about causality in the context of deep nets and system one, system two dichotomies of reasoning, and then Shokov I think is kind of leading everybody when it comes to integrating causal inference and causal inference theory with machine learning. So I was excited when this paper came out, and I want to see what's going on here. But I think it's good to start with the post, see what blog posts are designed to be more accessible. So let's see what the papers are, but let's see what the blog post says. Great. So when we look at, we see a picture of, we see a DAG, we see our neural net. Great. Look at the follow short video. You can make inferences about causal relations between different elements. For instance, you can see that the bat and the baseball's arm are moving in unison, but you also know that it is the player's arm that is causing the bat's movement and not the other way around. You don't need to be told that the bat is causing the sudden change in the ball's direction. Likewise, you can think about counterfactuals, such as what would happen if the ball flew a bit higher and didn't hit the bat. Great. Such inferences come to us humans intuitively. We learn them at a very early age without being explicitly instructed by anyone and just by observing the world. See, what's interesting about this is it kind of gets to some of that core thinking between that's underlying kind of say computational cogsi, symbolic AI, which is that we have these. We're looking towards human reasoning processes, human intuition as kind of the gold standard for how inference should work, which is notably different from, I'd argue is different from how deep learning engineers think, which is kind of a radical empiricism point of view, but also it's different from how causal inference people think, which is kind of objective truth kind of view. Like, you have data and you have some statistical assumptions, and you're trying to get to some truths that are basically deduction given those assumptions in the data. So induction in the form of going from assumptions to deductive conclusions through data. And so it's a very kind of objectivist point of view. Well, here we're talking about, let's reverse engineer human intuition, and that's the space I like to be personally. I think that's that's how we get science fiction computers telling us how to make better decisions, kind of like I don't know, Cortana or something like that. So, but for machine learning algorithms which have managed to outperform humans in complicated tasks such as Go and chess, causality remains a challenge. Machine learning algorithms, especially deep neural nets, are especially good at ferreting out subtle patterns in huge sets of data. See, I love this kind of language here. You always see it in, you want to say something about the limits of deep learning. You know that if you start talking about that, then you'll get a lot of pushback from people who are defensive of the well-earned accomplishments of deep learning. And so you have to really kind of start by saying what deep learning is awesome at in order to draw a line between what it can and can't do. So it's very good. I like this ferreting out. In other words, it finds subtle, nonlinear, high-dimensional statistical correlation. They can transcribe audio into real time, label thousands of images of video frames per second, and examine X-ray and MRI scans for cancerous patterns. But they struggle to make simple causal inferences like the ones we just saw in the baseball video above. In a paper called TORS, Causal Representation Learning, researchers at Max Planck and Milla and Google Research discuss the challenges arising from the lack of causal representations in machine learning models and provide directions for creating artificial intelligence systems that can learn causal representations. This is one of the several efforts that aim to explore and solve machine learning's lack of causality, which can be key to overcoming some of the major challenges the field faces today. And it looks like that heads to a Gary Marcus link. Let's just see what these major challenges are. Okay. Same author talking about limits, challenges, deep learning, Gary Marcus. Okay. Data hungry, data learning is shallow. Ooh, got a video. What's that say?
Welcome back, Seth Bling here. You're watching a skilled player play Super Mario World, but this player is not human. It's a computer program I wrote called Mario. This program started out knowing absolutely nothing about Super Mario World or Super Nintendo's. In fact, it didn't even know that pressing right on the controller would make the player go towards the end of the level. It learned all of these things through a process called neuroevolution.
I think I've seen
In this video, I want to teach you about how Mario learned to beat this level, Donut Plains 1, what his brain looks like, and how it's all based on actual biological evolution. So let's start out by actually looking at Mario's brain. Let's play it again, but this time we'll look at Mario's brain as it's making the decisions of what buttons to press. It's going to look a bit complicated at first, but don't worry, I'll break it down for you. This structure of colored lines and blinking boxes is called a neural network. It's a simple mathematical model for how a brain works, but it can produce some very complicated behavior. With enough computational power, a neural network could come close to simulating a real human brain, but modern technology isn't there yet. On the left side, you have the inputs. This is what Mario sees. It's a simplified view of the level. The white squares stand for blocks the player can stand on, and the black square.
Great. So this is playing Mario. Doesn't mean the AI algorithm has the same understandings as humans have of different elements of the game. For instance, if you look at 226, where a ball is thrown at Mario, most novice gamer would know that they would have to jump, but the AI keeps running until it gets hit in the back.
The player starts walking right. Behavior isn't complicated, but it's enough to make at least some progress in the level. Let's take a look at a sample neural network.
Moreover, if you gave that algorithm a new name, such as Super Mario 64 or Mega Man, it would have to learn a new game. Yeah, all right. So it doesn't generalize. It does, and it doesn't learn. It doesn't learn the abstractions in the game, and such that it could deal with slight variations to the levels that it's playing. Deep learning is opaque. So right, we can't explain them, and then great. So we've seen all those papers. So let's just let's go back. So what do we have here? IID data. Why do machine learning models fail at generalizing beyond narrow domains in training data? Machine learning often disregards who's saying this. Do we have a quote? Machine learning often disregards information that animals use heavily. Oh, this must be from the paper. Interventions in the world, domain shifts, temporal structure. By and large, we consider these factors a nuisance and try to engineer them away, write the authors of the causal representation paper. In accordance with this, the majority of current successes of machine learning boil down to large-scale pattern recognition on suitably collected IID data. I don't know if it has to be IID though. I mean, like, I guess it depends. Well, it depends on what the inference problem is and what the I've seen whether or not the data is identically distributed or independently distributed, rather, I think depends on how you define the problem. But even when it's not, neural nets do great because they'll just model the dependence somewhere in a hidden network. But anyway, IID is a term often used in machine learning. It supposes that random observations in a problem space are not dependent on each other and have a constant probability of occurring. The simplest example is flipping a coin or tossing a die. The result of each new flip or toss is independent of previous ones, and the probability of each outcome remains constant. So this conversation, I'm new to this paper, this blog post, and I haven't read it yet. So the fact that we're shifting into a conversation about IID is odd to me. I mean, I don't know why. I'm trying to understand where they're going with this. I'm trying to predict forward as I read, kind of like forward generate this paper in my head. And I'm trying to understand the connection between, I mean, obviously most statistical, like causal inference methods, like estimators, often rely on an IID assumption, but I'm wondering what the connection is to the implication here is that the lack of IID data is what makes it difficult for traditional or deep learning, for example, to reason about causality. Trying to predict that argument in my head, but I'm not seeing it. Let's see what happens. When it comes to more complicated areas like computer vision, machine learning engineers try to turn the problem into an IID domain by training the problem on a very large corpora of examples. The assumption is that with enough examples, the machine learning model will be able to encode the general distribution of the problem into its parameters. But in the real world, distributions often change due to factors that cannot be considered and controlled in the training data. All right, so we have a little bit of data drift. Okay, great. So if we have data drift, then if you have a causal model for why it drifts based on some latent causal variable, and you model that, then you can handle it, I guess. I guess that's what we're getting at. So we're just talking about, so IID here is talking about the assumption of no latent confounders, which is a term of art in causal inference. It just means that you have no unaccounted for causes that you're not modeling. So that assumption is violated, I guess, in a lot of machine learning. For instance, convolutional neural networks trained on millions of images can fail when they see objects under new lighting conditions or from simply different angles or against new backgrounds. So what are we looking at here? So different. All right, so we changed lighting, different angles, new backgrounds, and then what happens? All right, so we train it, and then we have this latent variable here of the lighting condition, and if we change that, then things break. I don't know what this picture is supposed to do. So we got, okay, so these are all chairs that are kind of rotated to be a little bit different from how they're usually, like they're on the floor, they're not standing upright. Here we're varying the background, so living room, like I don't know, is that a kitchen? Bedroom, bathroom, viewpoint. So now we're maybe changing the angle of the camera. Teapots, well, I don't know what's going on with t-shirts. So that's like, all right. are these? All right, I don't know why there's t-shirts here. All right, so efforts to address these problems mostly include training machine learning models on more examples, but as the environment grows in complexity, it becomes impossible to cover the entire distribution by adding more training examples. So this is a very good point. Like the way you deal with a problem like this in deep learning is by getting more examples that represent the variety of things that can happen. So right, if in my training data I have all the chairs sitting upright, then I need to, but then it gets confused by chairs that are not sitting upright. Then I just need to add more chairs that are not sitting upright to my training data. And so what that means is that you think about that in terms of workflow. You train a model, you find out only after you spent quite an amount of time and compute and money training said model, potentially you're spending a lot of money. You see what the failure modes are, and then you go back and collect more data, which might be expensive. Or even if you have access to a lot of data, you have to curate it. You have to say like, okay, well, which are the pictures that are of chairs that are not standing upright? So maybe you have to find some gig workers, or you have to have somebody who's going to go sit through a large pile of data to find examples of where the model is failing, so that you can feed them back into the training of that. And then you have to retrain. You can't even, I mean, I guess you can take the original network and use it as parameters as the seed for the next stage of training, but you can't just train a separate component of a model for these new examples and then glob them onto the original model. And so that's less than desirable. And again, if you have the resources to make it work with deep learning, then great. Most people don't. Most companies don't have that size of data. And even if they did, getting it labeled and curated with respect to a specific problem that you're trying to solve is a lot of work. Lack of causal understanding makes it difficult to. This is especially true in domains where AI agents must interact with the world, such as robotics and self-driving cars. Lack of causal understanding makes it very difficult to make predictions and deal with novel situations. This is why you see self-driving cars make weird and dangerous mistakes. Let's watch what happens here. What's going on? There's a truck on the road. Oh, I can see this guy's gonna crash in that truck. Who is that? Oh, stop. Oh my God, man, I hope, did somebody die? Or is that just the empty car? Tesla Model 3. It just plowed right into it, man. Was that another one? Okay. Wow. That's wow. Like what? It just seems like it seems like a straightforward, like there's an obstacle right there. Huh? Well, okay, so after training millions of miles and made that mistake, that's pretty damning. Like it's not even like, for example, like that one case of that woman, what was it, in Arizona, getting hit by a car and kind of late at night, but she's running across the highway in the middle of the night. It's kind of like, well, that sucked. What's going on? It's on this. Oh wow, we got another angle. Let's see what that looks like. Wow, did it even slow down? Is there any? Wow, there's no lights. Maybe I can't. Maybe are these? Can you see lights on these cars? Yeah. There's lights. Huh. Well, I can't see the lights that. So maybe it slowed down a little bit. But it looked almost as though. I can't really see. It's almost as though it didn't even slow down. Generalizing well beyond IID settings requires learning not mere statistical associations between variables, but an underlying causal model. The AI researchers are right. Actually, if somebody doesn't mind, I see there's a few people watching. If you wouldn't mind writing a comment I think I'm looking at a comment box, but I want to make sure that I can that things are showing up if they are. Don't want to miss anything. There's supposed to be like a thing here. It's supposed to show me. View. Overlays. I don't know. There's so many options on this thing. Anyway. Yeah, I should just go get this thing set up and just have it be click button ready. Oh, no, somebody said hi. Thank you for doing that. Yeah, I feel less crazy now. Let's see here. So generalizing well outside of IID settings requires. So what? See, okay, I guess yeah. So there's some confounding here. It's interesting characterizing that as an IID problem. I guess, while technically true, not the way would have occurred to me to phrase it. All right, so causal models, and again, this author, who is this? Ben Dixon. So I don't. Who's Ben Dixon? Maybe he's a software engineer and founder of Tech Talks, University of Technology, Politics, and Business. Well, all right. But he might be. I don't know if he's. Well, you know, he's quoting them verbatim, so I assume that's what they wrote. All right, so causal models also allow humans to repurpose previously gained knowledge for new domains. For instance, when you learn a real-time strategy game such as Warcraft, you can quickly apply your knowledge to other smaller games, StarCraft or Age of Empires. Transfer learning in machine learning algorithms, however, is limited to very superficial uses such as fine-tuning an image classifier to detect new types of objects. In more complex tasks such as learning video games, machine learning models need huge amounts of training, thousands of years worth of play, respond poorly to minor changes in the environment, example, playing on a new map or with a slight change to the rules. When learning a new causal model, one should require fewer examples to adapt as most knowledge, i.e. modules, can be reused without further training. That's true. The authors of causal machine learning. So this is true of, causal models is that the assumptions that underpin causal models enforce a certain kind of modularity that allows you to take components of the model and apply them in new settings. So why has IID remained the dominant form of machine learning despite its known weaknesses? Pure observational-based approaches are scalable. You can continue to achieve incremental gains in accuracy by adding more training data, and you can speed up the training process by adding more compute power. In fact, one of the key factors behind the recent success of deep learning is the availability of more data and stronger processors. True. All true. I was going to say something. What was I going to say? You know what? And there's another reason. I think there's a cultural reason, which is that, people feel a bit icky. When we talk about this structured knowledge, you have to come up with the structure. You can learn it from data, but even that requires some inductive biases that are not just, not inductive biases that you get for free out of a magic neural net architecture, but inductive biases that you have to articulate in terms of domain knowledge as a person, as a human, as an agent who reasons about the world. And that flies right in the face of the radical empiricist attitude of most deep learning engineers. But my experience with working in deep learning is that people are happy to work in prior knowledge just as long as they don't have to construct some new knowledge artifact each time. If for example, you could say, just if the process is simply repeatable, so rather than, if for example, I could say, hey, learn a structure from this data with this inductive bias, and even if I have to kind of articulate the inductive bias, it's fine if the entire workflow doesn't need to change each time I fit a model. But for the most part, causal modeling, I mean, it could do that, but nobody does that. So I mean, I think that's one point that a lot of the researchers miss, is that people, like engineers, are happy to bring in prior knowledge as long as they don't have to hand craft a bespoke model each time. That was an insight from one of my students and friends, Payam, actually. Yeah, it's interesting. Anyway, so ID-based models are easier to evaluate. Take a large data set, split it into training and test. Great, so we've got cross-validation. Continue the training until you reach accuracy. There are many public data sets to provide benchmarks, such as ImageNet, CIFAR-10, MNIST, and there are also task-specific data sets, such as COVID-X dataset for COVID-19 diagnosis and the Wisconsin breast cancer diagnosis dataset. In all cases, the challenge is the same: develop a machine learning model that can predict outcomes based on statistical regularities. Right, so we tend to pick our problems based on how easy they are to evaluate. I remember, kind of my earliest machine learning courses back in grad school. Professor, don't remember his name. I think he was famous for having worked on collaborative filtering. That narrows it down quite a bit. I'm not embarrassed to say that guy was kind of a jerk. But anyway, so I remember taking his class and jerking us aside, like I'd come up with these kinds of interesting problems that I wanted to model and solve, but for the class projects, but they wouldn't let me work on them because it wasn't clear how you would do the evaluation, which is fine, right? Like, what's the point of working on something if you don't know how well you're doing? On the other hand, it biases you, especially if evaluation requires these kind of large data sets that are hard to come by, and so you kind of work with the same set of data sets, and it means that you're biased towards problems that have this kind of evaluation, and likely to ignore problems that would be very valuable to solve with machine learning, but you don't really know how to tackle that problem because there's no way that you can evaluate it, and thus there's no way you can publish a paper on it because the reviewers would say, well, how do we know it works? But as AI researchers observe in their paper, accurate predictions are not sufficient to inform decision making. For instance, during the coronavirus pandemic, many machine learning systems began to fail because they had been trained on statistical regularities instead of causal relations. As life patterns emerged, the accuracy of the models dropped. Life patterns. This is something that always kind of shocks me that people are surprised about. We had even before any of this, causal inference became ubiquitous, the idea that, so your accurate predictions are not sufficient to inform decision making. People have known that forever. If you work in finance and you're going to start training algorithms that's going to maximize expected return, you're going to get fired. Because everybody who does quantitative finance knows that you need a much more sophisticated loss function if you're not going to bankrupt your company. Say, for example, a minimax loss function, one that minimizes the maximum amount of, rather than maximizing the expected reward or expected return, or minimizes the expected loss, you minimize the maximum amount of loss that you can make, or something akin to that. In other words, it's only, I don't know why all of these many decades of decision theory and operations research are lost to AI researchers. Probably because we just kind of look at these data sets and just figure out and just think about it in terms of accuracy, right? And don't think about what happens when we fail to classify breast cancer, or we succeed in classifying breast cancer, or we we predict somebody has breast cancer and recommend some kind of treatment that's going to be, there's no breast, most breast cancer treatment is quite severe, right? And so like imagine prescribing a treatment based on an algorithm that got it wrong, right? Like that kind of cost of a false positive is really never considered when we look at these evaluation sets. And I don't know why. I mean, I think some people think about this, but it's probably more of a convention than anything else. Yeah, so some of these comments. Sorry, this was, I need to get in the habit of looking back and forth to comments. So like, ease of use, building a DAG takes time. That's true. So like, building a DAG takes time, training a net takes time, and I guess if you got two things to do, you train a neural network, you got to optimize the hyperparameters, and there's a lot of fine tuning involved. And so if you got to spend time on one thing, I guess, it's hard to convince somebody this, I got all this work to do in terms of getting this neural network to work. And so like, if you're asking me to do yet another modeling task, it's a big ask. What was machine learning systems? Statistical regularities, but as AI researchers observed in their paper, accurate predictions are not sufficient to inform decision making. For instance, we did that already. Causal models remain robust when interventions change the statistical distributions of a problem. For instance, when you see an object for the first time, your mind will subconsciously factor out lighting from its appearance. That's interesting. So we're going back to the cognitive science. So I see an object, and when my mind is kind of thinking about that, it's processing that object, it's disregarding lighting or the Coke stain on the surface of it or something like that. So that's why in general you recognize the object when you see it under different lighting conditions. Causal models also allow us to respond. So like that's a good example with the cars, right? Like with that woman who got hit at night, it's possible like the car hadn't seen that much nighttime images of pedestrians, and so it just didn't know that was a pedestrian because it doesn't, it's looking at these patterns, but it doesn't actually kind of conceptualize pedestrian. Causal models also allow us to respond to situations we haven't seen before and think about counterfactuals. We don't need to drive a car off the cliff to know what will happen. Counterfactuals play an important role in cutting down the number of training examples a machine learning model needs. This reminds me of, I often see this like as the argument for causal reasoning presented to machine learning people, which is you need less training data, which of course is a very compelling argument because training data is expensive and it requires more computation. It kind of feels to me sometimes like, it's like the benefits of marriage being described as you get a better tax deduction. That's just the first place I would go to when I think about why one ought to get married. But there you have it. The other thing this reminds me of is kind of a different argument, a different kind of convincing that had to happen to get statisticians to adopt causal methods. So before people gradually started, in the statistics community, gradually started adopting causal inference as a thing, they basically kind of hand-waved away confounding and said, kind of described it in terms that are a bit convoluted and said that you address it using randomization in controlled experiments. And I remember reading, I hope I can get this right. The idea was that imagine how little we would have accomplished as a society developing technology, like how paltry our technological developments would have been if we relied on randomization to infer causality, right? And to infer causal effects, right? Like, because there'd be so many things you couldn't do. Like, how would they have developed the parachute? Would they have, to say, okay, let's connect these people to a tarp, and then we'll connect, and then these people will be connected to nothing, and we throw everybody out of an airplane and see what happens. That experiment probably wouldn't have been approved by whatever board approved such things. But it was, you start by kind of thinking like, okay, well, let's think causally about drag and all of that, and let's run and let's try a few things, and eventually somebody had to jump out of a plane, right? Without knowing fully, probably without having, without running a randomized experiment where you had people in some control group who were, jumping out of a plane with some kind of control parachute. Anyway, causality can also be crucial to dealing with adversarial attacks. So this is one thing I've often thought was pretty interesting. Nobody really talks about. I saw a few papers about this at NeurIPS once. Although they didn't actually put it in causal terms, but they were talking about it in a way that seemed obviously causal, like obviously counterfactual, right? The idea that anyway, let's see what they say. Subtle manipulations that force machine learning systems to fail in unexpected ways. These attacks clearly constitute violations of the IID assumption, while that underlies statistical machine learning. The authors of the paper write, and adding that adversarial vulnerabilities are proof of the differences in the robustness mechanisms of human intelligence and machine learning algorithms. The researchers also suggest that causality can be a possible defense against adversarial attacks. So this is a famous example where they add a little bit of white noise to this image that previously was classified as a panda with 57.7 confidence. And I don't know what nematode means. Oh, okay. So this is white noise, which is clearly not a nematode. But this white noise example was constructed through an adversarial attack, an adversarial technique. In other words, you kind of you take this model and you try and figure out, like, using by observing gradients, what small changes to this image can I get before the classifier classifies it as a given, and you then you collect all those small changes and basically this is the diff between this and this. And so it's interesting because in the human eye, so the changes are so small that the human eye cannot actually detect the difference between, you can't look at this and be like, I can't look at this at least and see and think that this is any different from that. But evidently the algorithm sees this and thinks it's a given. Not only that, but with high confidence. And I have seen some papers that are looking for that try to find techniques that prevent this. Like I think one, for example, was when I was trying to classify faces. It constructed some kind of training procedure that looked towards. It basically had constrained the neural net such that its classification of the face was focused around the eyes and the nose and the mouth of a face, right? And so it's basically saying like, okay, these only focus on these patterns of pixels when trying to classify a face. And it was interesting because that's essentially a counterfactual question, which is that, like, all right, well, I have some pixels that I think might be a face. Like, if these pixels were so if this were not a face, would I still see this? What's the probability I would still see these kinds of pixels? And so, like, the probability of those pixels around that together form an eyes and nose and mouth will be high, and the probability of pixels that are not would be lower, and so like it was, and so it was interesting because that immediately jumped out to me, although I don't think the researcher was thinking about it in those terms. Hope they are now. In a broad sense, causality can address machine learning's lack of generalization. It is fair to say that much of the current practice of solving IID benchmark problems and most theoretical results about generalization in IID settings fail to tackle the hard open challenge of generalizing across problems. Adding causality to machine learning. In their paper, I need something to drink. In their paper, the AI researchers bring together several concepts and principles that can be essential to creating causal machine learning models. Two of these concepts include structural causal models and independent causal mechanisms. So independent causal mechanisms is a really interesting kind of area of causal models that Bernard Shokov works on. And the idea here is that we have this idea in causality called Reichenbach's what? I think it's this Reichenbach's principle or Reichenbach's law. But it's just that if you observe some kind of correlation, then either, say a correlation between A and B, then either A causes B or B causes A, or they have a common cause. There's also a fourth case, but gets a bit nuanced. Anyway, we can just assume that those three cases. And so which means that if we actually have a causal relationship, like A causes B and B causes A, we can kind of fit this this model of the statistical model of the correlation between A and B. But because A and B, behind A and B's relationship is some actual real world causal mechanism that doesn't depend on context. It's just like if A causes B in Norway, then A causes B in Denmark. So, or I don't know, a non-Scandinavian place like Mexico. And so the idea then is that the mechanism itself is independent of the context. And so once you understand that, there's a whole bunch of things you can do. There's a bunch of ideas from information theory and computer science that you can bring to bear on that idea. Heck, even theoretical physics, you can bring to bear on that idea and kind of basically use the presence of independent causal mechanisms as a kind of inductive bias in inference. So in general, the principles state that instead of looking for superficial statistical correlations, an AI system should be able to identify causal variables and separate their effects on the environment. This is the mechanism that enables you to detect different objects regardless of view angle, background, lighting, and other noise. Disentangling these causal variables will make AI systems more robust against unpredictable changes and interventions. As a result, causal AI models won't need huge training data sets. Once a causal model is available, either by external human knowledge or a learning process, causal reasoning allows to draw conclusions on the effect of interventions, counterfactuals, and potential outcomes. The authors of the paper write. The authors also explore how these concepts can be applied to different branches of machine learning, including reinforcement learning, which is crucial to problems where an intelligent agent relies a lot on exploring environments and discovering solutions through trial and error. Causal structures can help make the training of reinforcement learning more efficient by allowing them to make informed decisions from the start of their training instead of taking random and irrational actions. Whenever people ask me about reinforcement learning, causal reinforcement learning, I always point them to causal decision theory. What Markov decision processes are just sequential decisions. And so when it comes to an individual decision, we have this interesting body of work called causal decision theory, and arguably, if you're just kind of fitting a statistical model or model-free approach to reinforcement learning and then maximizing reward, you're doing evidential decision theory. And so all you really have to do to understand what the benefits of bringing a causal approach to just reinforcement learning would entail is to just take just look at this research on the difference between evidential decision theory and causal decision theory. And it'll show you a few examples. One like Newcomer's problem. Is that in here? Newcomer's paradox. Newcomer's paradox, for example, is a simple game that becomes a use case for why, or rather a case study for why causal decision theory might be preferred to evidential decision theory. It's a case where these two different decision-making approaches will lead to different outcomes, but it's not a very, it's not a very common example. Somebody gave me an example the other day with a bandit algorithm and Thompson sampling, but I have to write it up before I'm able to talk about it again. The researchers provide ideas, but like this kind of not doing random irrational actions is kind of illustrated a little bit in that Super Mario example we saw, where they're not, so Mario doesn't need to get pegged in the back of the head of a baseball before he figures out the jump. Like he should have some kind of, his decision not to jump or to jump should be informed in some way by a causal model. Or even components of a causal model that he's learning as he goes, right? So you can learn causal models to some extent from observational and intervention data. An agent, from the results of actions of an agent in its environment, and then you can kind of update that model as you go while using what you've learned so far to make decisions, to choose new actions. The researchers provide ideas for AI systems that combine machine learning mechanisms and structural causal models. To combine structural causal modeling and representation learning, we should strive to embed an SCM into larger machine learning models whose inputs and outputs may be high dimensional and unstructured, but whose inner workings are at least partly governed by an SCM. That is exactly what I think. Wow, now I'm a bit spooked because I thought I was the only one who was like trying to generalize SCMs to generative models, but I guess Yasha Bengio is too, so I'm a bit worried. The result may be a bit modular, be a modular architecture where the different modules can be individually fine-tuned and repurposed for new tasks. Such concepts bring us closer to the modular approach the human mind uses to link and reuse knowledge and skills across different domains and areas of the brain. It's worth noting, however, that the ideas presented in the paper are at the conceptual level. As the authors acknowledge, implementing these concepts faces several challenges. In many cases, we need to infer abstract causal variables from available low-level input features. There is no consensus on which aspects of the data reveal causal relations. The usual experimental protocol of training and test sets may not be sufficient for observing and evaluating causal relations on existing data sets, and we may need to create new benchmarks, for example, with access to environment, information, and interventions. Even in the cases we understand, we often lack scalable and numerically sound algorithms. But what's interesting is that the researchers draw inspiration from much of the parallel work being done in the field. The paper contains references to work done by Judea Pearl, I think it's pronounced Yuda actually, Yuda Pearl, and a Turing Award-winning scientist best known for his work on causal inference. Although that's not what he won the Turing Award for, incidentally. Pearl is a vocal critic of deep learning, pure deep learning methods. Meanwhile, Yasha Bengio, one of the co-authors of the paper and another Turing Award winner, is one of the pioneers of deep learning. The paper also contains several ideas that overlap with the idea of hybrid AI models proposed by Gary Marcus, which combines the power of symbolic systems with the pattern recognition power of neural nets. The paper does not, however, make direct reference to hybrid systems. The paper is also in line with System 2 deep learning, a concept first proposed by Bengio in a talk at the NeurIPS 2019 AI conference. The idea behind System 2 deep learning is to create a type of neural net architecture that can learn higher representations from data. Higher representations are crucial to causality, reasoning, and transfer learning. While it's not clear which of the several proposed systems will help solve machine learning's causality problem, the fact that ideas from different and often conflicting schools of thought are coming together is guaranteed to produce interesting results. Okay, now we're wrapping it up. At its core, IID pattern recognition is but a mathematical abstraction, and causality may be essential in most forms of animate learning. Okay. Until now, machine learning has neglected a full integration of causality, and this paper argues that it would indeed benefit from integrating causal concepts. So great. So this is really just having some big names from, well, we got Shokov and Bengio and some Googlers saying some important things that people have kind of already been saying for a while. Reichenbach principle, that's what it is. Reichenbach principle, not rule. Anyway, there you go. C, structural causal models. Good. So we're explaining a lot of these ideas. The independent causal. So this is independent causal mechanisms. I think is really interesting stuff. It just really kind of has so many connections to statistical kind of, especially information criterion, to what do we call it? To minimum description length, or I guess you would call it algorithmic complexity theory in computer science, thermodynamics and physics. So I really get excited when I hear Bernard Shokov and people in his orbit. Well, I should say people who are working with him, rather. It sounds a bit pejorative to call it an orbit, but that are working on these things. Causal discovery, machine learning. I did my PhD on causal discovery, and I just, whenever I see it again, I just feel like, oh my God, I don't want to do this anymore. What we got here? This paper looks like a winner. Semi-supervised learning. So Shokov has a really good example for how semi-supervised learning works only when you are where the data, the features are the effect, and you're trying to learn you're trying to infer the label, which is a cause. If the label is if the data is the cause and the label is the effect, then it won't work. I thought that's a really interesting contribution. What we got here is got some what are we doing here? Empirical risk. We're talking about what are we talking about here with robustness and generalization? Okay, so this is an area. So here we're trying to figure out looking at trying to evaluate the loss function for how well it'll generalize. That's interesting work. So this looks like it's looking like a summary of a review of the various applications of causal reasoning in machine learning tasks. So let's conclude here. The conclusion, the last 2 minutes. In this work, we discussed different levels of models, including causal and statistical ones. We argued that this spectrum builds upon a range of assumptions in terms of modeling and data collection. In an effort to bring together causality and machine learning research programs, we first presented a discussion on the fundamentals of causal inference. Second, we discussed how the independent mechanism assumptions and related notions such as invariance offer a powerful bias for causal learning. Third, we discussed how causal relations might be learned from observational and interventional data when causal variables are observed. Fourth, we discussed the open problem of causal representation learning, including its relation to recent interest in the concept of disentangling representations. Finally, we discussed how some open research questions in the machine learning community may be better understood and tackled within the causal framework, including semi-supervised learning, domain generalization, and adversarial robustness. Based on this discussion, we list some critical areas for future research: learning nonlinear causal relations at scale, learning causal variables. So this is like latent variables that we're trying to disentangle. Probably trying to use that idea of the independent mechanism as a way to tackle that. Understanding the biases of existing deep learning approaches, learning causally correct models of the world and the agent, and that's it. Cool. Any questions? Otherwise, I'm gonna go. Well, awesome. I don't know. There's probably a bit of a lag, so I'll wait maybe 5 more seconds. Well, all right then. Have a good Tuesday.